So where I last left off, I was saying that the sum of the areas of all these rectangles is equal to f of b minus f of a. So let's go over that again. So the sum of the areas of each of these rectangles. And each of these rectangles has dimensions delta x as its base and f prime of x as its height for each of the various values of x along this interval. Each of these values of x that is subdividing this interval, right? And so, because the dimensions of the rectangle, of each one of the rectangles is f prime of x and delta x, then the area of the rectangle is f prime of x times delta x. And from what we looked at when we looked at these points closely, we realized that delta y, which is the increase, the vertical increase from one point to the next, is approximately equal to the derivative at each point, the derivative at x, multiplied by the horizontal change, delta x. And again, this is because, like I said, because slope, if the slope is f prime of x is the rise over the run, and the run here is delta x, right? Then the rise that we would expect then after we move across delta x is f prime delta x. And this is of course an approximation of delta y, which is the total vertical increase from this point to the next. So delta y, for each one of these points, delta y is approximately equal to f prime of x times delta x. And then we established at the very beginning that all of these delta y's, all of these vertical increases, if we add them all together from one point to the next, the sum of all of them should be the total vertical increase from the beginning of the interval to the end, from a to b. F of b minus f of a, right? That expression, which gives us the total increase. So again, we have the sum of the areas of rectangles. The rectangles are designed so that the area of each one is equal or approximately equal to one of the vertical increases. Summing up the areas of the rectangles is equivalent or approximately equivalent to summing up each of these vertical increases, such that the total sum of all these areas is equal to this total of vertical difference between these 2 points, right? And we did this with 8 rectangles. We split up the interval a to b into 8 subintervals, and we found 8 rectangles, 1 rectangle for each subinterval. Right. So now let's look at what happens as n goes to infinity. So as n goes to infinity, we have more and more rectangles, and we have more and more rectangles let's take a step back. As n goes to infinity, we have more subintervals, because n is the number of these subintervals. We have more subintervals, which means that each of these subintervals is now a little thinner, right? Is a little less wide. So delta x goes to 0 as n goes to infinity. And one thing we should notice is that as n goes to infinity, and as this as delta x, as the width of these intervals becomes smaller, that delta y becomes closer and closer to f prime of x times delta x, right? Because as of course delta x and delta y go to 0, then it becomes f prime of x is the derivative, of course, and delta y over delta x will give you the derivative. But basically, this approximation becomes more and more accurate as delta x decreases. As these 2 points become closer and closer together, this delta x times f prime of x becomes closer and closer to delta y. Right, so f prime of x times delta x becomes closer and closer to delta y. And now let's see what happens to these rectangles. So these rectangles that we constructed, as delta x is now becoming closer and closer to 0, so the width or the width right here of each of these rectangles is becoming skinnier and skinnier. Each of the rectangles is becoming skinnier and skinnier. And what we notice, this fascinating thing begins to happen, is that we have these thinner and thinner rectangles, and instead it starts to look less like a bunch of rectangles next to each other, and it starts to look more like a curve. The tops of the rectangles begin to form a sort of a curve. Because, as we're saying, as n goes to infinity, basically you have a bunch of infinitely thin rectangles. And these infinitely thin rectangles, what they do is they seem to form the area under a curve. And if you remember, when we're trying to find the area under the curve, what we do is we split it into a number of rectangles. And we split it into a finite number of rectangles, and we see what happens as that number goes to infinity. That's basically what's going on here. We have, as n goes to infinity, these rectangles become thinner and thinner and thinner, and they better fill up this area under this curve right here. So what is this curve actually? Well, we know that for each of these rectangles, the height of the rectangle is f prime of x for each value of x. So if you think about it, you can start to see that this curve is actually the graph. It's actually the graph of f prime of x, right? Such that if you look at each of these points along this curve, the y-coordinate of each of them is f prime of x, so that the height, if we split it into rectangles, the height is f prime of x. So you can slowly see, as we increase n, these rectangles begin to start to form this area under this curve. So these rectangles ultimately are just an approximation of this area under the curve. And as n goes to infinity, we get more and more accurate. So to get this area under this curve. I'll leave you a few seconds just to digest that. So again, what we did was, we said that as we have more and more intervals, as we have these really, really thin intervals, we have these really, really small horizontal and vertical changes, then we are better able to approximate, or better able to describe the vertical change with this equation right here, basically. Where delta y, f prime of x, times delta x becomes closer and closer to delta y. And then what we did was we constructed this geometric representation of all of those delta y's, we constructed rectangles essentially. And as n goes to infinity, the sum of the areas of all those rectangles, or basically the sum of the total area under the curve, is equal to this total vertical distance. So this statement, that f of b minus f of a is equal to the area under the curve of f prime of x from a to b, or in other words, the definite integral from a to b of f prime of x. This is known as the fundamental theorem of calculus. And I hope that I at least provided some intuition for why this might be true.